location. So here is an example. Here are some examples of free-wave bottlenecks. At the places of merging or lane reduction or weaving, there may be bottlenecks. And these are the places that should have bottleneck. And if you see bottlenecks around here, that would be normal, and you can measure those capacities. These are the ideal places of measuring capacities. Now the third step is to select these calibration parameters. You want to calibrate your model, and you know the capacity, and you know your model's capacity. But what can you do? What's your tool? You have to select some calibration parameters, and by changing these parameters, you are going to make the two capacities match. First, let's talk about free-wave facilities. For free-wave facilities, we have more than three parameters to change. But here I only listed three as examples. To get a full list, you have to check your software manual. Okay. So the first parameter we can change is called mean following headway. That is the desired headway between the vehicles traveling. So it is equal to how much distance you want to keep. Between you and the vehicle ahead of you. And I want to ask you, how does that affect the capacity? I don't want you to calculate that, but you can try to do it in a qualitative way. So when you increase this headway, will the capacity increase or decrease? This has to be answered. How does this mean following headway affect the capacity? Why? Can somebody answer me?
So the headway increase, so the capacity decrease.
Yes, that's right. You are right. Very good. So the headway means the distance, the gaps between vehicles, and the volume is calculated by the speed multiplied by density. When the headway increases, the density decreases, and therefore the volume also decreases, right? So that's easier to understand. Now, driver reaction time. Driver reaction time is used in car volume model. I haven't introduced car volume model yet because I want to fully introduce how to before I talk about why. In these lectures, actually in the beginning I was planning to talk about these models first, but later I changed my mind because I think after you understand how to, it will greatly benefit you to understand why. So that's why I haven't introduced these car volume models. But I can tell you the driver reaction time means when you see the vehicles ahead of you change their speed. After this reaction time, you will change your speed. Okay? Reaction time, driver reaction time. So how do you think this parameter affects the capacity? Here I have a picture of a spring. So that may help you understand it. So how do you think the driver reaction time affects the capacity? Any idea? If the reaction time gets longer, or if the reaction time gets shorter, how do they affect the capacity? Here is the analogy. So why did I use this? Let's think about a platoon of vehicles, and ideally they are traveling at the same speed, so they are going to keep this mean following headway. But suddenly, one vehicle changes speed. Let's suppose all the vehicles are having 0-second reaction time. Then all the following vehicles are going to change their speed instantly. So their relative headway will not change. Using this example, that is the spring example, you will mean that this spring cannot be, it's very hard, it cannot be compressed, right? Understand it? When the driver reacts immediately, for example, when you are driving, if the vehicle ahead of you changes speed and you have a 0-second reaction time, then your relative position will not change. Which means if you and the vehicle ahead of you represent a spring, then this spring will not be compressed. But let's suppose the driver reaction time is very low or very big. So the vehicle ahead of you stops, but it takes you 2 seconds to change your speed. That means this spring can be compressed, right? So how does that affect the capacity? That's my question.
So if a driver takes a longer time to respond, then the highway or the spacing will increase, right? Then the volume of vehicle will decrease.
You are right, but that's not 100% true. This depends. By changing this, actually the result will be the capacity or the capacity will change, but it may not increase or decrease. So let's think about a very soft spring. If you drag it, it will be longer. If you compress it, it will be shorter. So that depends on if you compress it or if you are uncompressing it. So this driver reaction time, when it gets bigger, will affect the characteristic of the vehicles, and that will make the capacity unstable. Okay, my conclusion is it will make the capacity unstable. So the vehicle ahead of you, let's suppose the reaction time, for example, is infinity, and we have only 2 vehicles. So the vehicle ahead of you increases its speed, but you are not increasing your speed. Then the density is decreased, right? So in this way, the capacity will decrease. But if your reaction time is 0 seconds, and the vehicles ahead of you increases, and you are also increasing your speed, and that makes the density unchanged. But if the vehicle ahead of you is stopped, I mean, let's talk about the infinity reaction time again. So the vehicle ahead of you stops, decrease its speed, but you don't react to it. Finally, you are going to collide, and your density becomes very big. And so these are 2 extreme cases. Are you clear about this? My conclusion is the increment of reaction time makes the capacity more unstable. So the third thing, critical gap for lane changing. Let's think about the multi-lane freeway. For changing a lane, for a vehicle to change its lane, it has to wait until there is a gap, a sufficient gap at the lane that it wants to change to. This is called critical gap. Let me draw it. I think this may be already demonstrated in racing. So 2 lanes, and this vehicle wants to switch left. And here is a vehicle at that lane, and this vehicle will not change to the left until this gap is long enough. So this is in the lane changing model. How does this parameter affect the capacity? Why does it affect the capacity? The critical gap.
If the critical gap is longer, then capacity will be lower because the density needs to be less.
Could you say that again? Sorry, I didn't quite understand.
For lane changes to occur, if the critical gap needs to be longer, then density has to be less, and so capacity would also be less.
But the problem is the critical gap doesn't it doesn't mean the mean falling headway. So you have a long critical gap, but your vehicles may still traveling, following each other at this mean falling headway. So the density is not changed. Then why does this affect capacity? Actually, you are on the right track, I think.
If one vehicle wants to change the lane and go to the gap and not enough, he will slow down. What will this vehicle do?
Right, that's the right track. So Inge mentioned that when the vehicle, for example, I'm giving an example. Let's suppose here is an exit. Here is exit that this vehicle wants to take. So this vehicle wants to exit here. As a result, this vehicle has to change left, right? And this vehicle will start changing left, like 1 kilometer or a certain distance before this exit. But because the critical gap is too big, and the mean falling headway is too small, so this vehicle cannot switch left. In the simulation software, this vehicle will proceed. It cannot switch left, it will proceed. But when it reaches this location, it may stop here to wait for a critical gap. And that will cause this lane blocked. Okay? So that's why the critical gap for lane changing will affect the capacity.
I was wondering why do we say that when what is the relationship between capacity and density? What is meant by that? You're saying that the capacity is a function of density?
No. I think I said it wrong. It's the volume is a function of density.
The volume, but the capacity is not a function of density per se.
Right, but capacity is the maximum flow rate.
Exactly.
Right. The maximum flow rate is calculated by the density multiplied by the maximum speed. If the density is a constant, then the maximum flow rate can be density multiplied by a speed limit.
Yeah, but the whole curve could change. I mean, why are you assuming that the speed would be constant?
The speed is not constant, but the speed is already coded in the network. The speed limit is coded. And the vehicles traveling are following a distribution of the speed. So we can, in this stage, in the calibration stage, we may want to assume it's already fixed.
Yeah, and I see what you're saying, but maybe it's not always the right way to think about how the density was changed, and that would change the capacity. But I mean, for example, for the critical gap, as you explained, I mean, it's the way that it would take longer for people to make lane change.
Right.
So they wouldn't have the flexibility to make lane changes, so they would drive slower.
Right.
Because they can't pass a slow-moving vehicle, and as a result, the capacity overall or the efficiency of the system would be